Okay then, so last time we looked at the shear forces in this beam internally due to the external loads and reactions. So we had a load of P at midspan, and that gave rise to reactions of P divided by 2 at each of the points. And just for completeness, we had a horizontal reaction of 0 at the fixed pin bearing at A, and the slider at B, where this is A and this is B. Okay, so we established a shear force diagram internally for those beams, where the shear forces were reacting or giving rise to internal equilibrium of the externally applied forces due to the actual load P and the reactions to that load at the supports at A and B, P upon 2, each of them. We're now going to look at the internal bending moment, which is given rise to from those external loads. So we have a beam which we are going to cut at some point. We're going to take a cut at some point between A and the mid-span point, and last time we said that gave rise to a shear force and a bending moment, Vx and Mx. Okay, and we said that the lever arm X to that point was given where this is a reaction P upon 2. That is the only external force at this section because we haven't yet reached the midpoint, so P hasn't come into play yet. So the moment, Mx, this time we're looking at the moments. Again, from our third equation of static equilibrium, we established that the sum of the moments about the z-axis at some point on the plane have got to equal 0. So we have bending moments due to, at this point here, we have, at this section, we have a P divided by 2, and then that is multiplied by X, so the distance along, and that has to be counterbalanced by so they are acting in the clockwise direction, and we then have a minus mx, which is this internal bending moment within the beam, have got to equal 0. So if we rearrange that equation, mx, which was the bending moment at a point x in the beam, where this is valid for locations where x is less than L divided by 2. So mx is equal to P divided by 2 times x. Okay, and that is valid up until the point where P comes into play, which is at a point on our beam distant from point A of L divided by 2. Okay, so that's the point on the beam at which this then becomes invalid. This is only valid for x is less than L upon 2, because that's the only region of the beam where P on 2 in the vertical direction applies. So we have this mx up to the point where x is P upon 2, and at that point where x is P upon 2, let's do that in black, mx is equal to P divided by 2 multiplied by x, which is equal to L divided by 2, which gives us P on 2 times L on 2 is PL divided by 2 2s are 4. Okay, so at the mid span, or where L, or X rather, is equal to L divided by 2, we have an internal moment of PL divided by 4. At other points, so let's start drawing that out for our beam. So this is our beam under a load P mid-span. We can say that the bending moment diagram, where X is 0, for example, the moment is 0 because P divided by 2 times 0 is 0. And we kind of know intuitively that we've got to be at 0 here because we've got a pin here which is not capable of providing a restraint, so we cannot get a internal moment within our beam. And that steadily increases as X increases up to the point at mid-span where this is equal to PL divided by 4, as we've calculated here. Okay, and also we know that X, as X linearly varies, so that the power of X is raised to is the power of 1, so it's not an X squared term, for example. So we know that that's a linear equation, so that linearly varies to PL divided by 4 as we move along the beam to this point here. Beyond that point, we then come into a situation where we have two forces to consider. So we're now in a situation where X is greater than L divided by 2, but less than, less than L. Okay. So we've not come to the full, so we're in this region between the application of the point P and the point B, which is our other reaction. So we have a point load here, we have a reaction here, and this distance is L divided by 2. And we're now saying that this X value here, so we now have a change in our equation, and again we are looking at a situation where we have some shear force in this beam, internal shear force, and an internal moment to resist these two forces due to, the shear force and bending moment due to that load P and this load at the reaction of P divided by 2. So those are our two forces. So we have an equation for those forces of P divided by 2 times X minus, because that's going clockwise, this is going anti-clockwise, minus P into X minus L divided by 2. So we've got this total X minus this L divided by 2 gives us the distance from P to our point of interest, which is some section between the point at which P is applied and the reaction at B, point B. For that, if we look at the solution of that, we end up with, or we can see that we've got this X term in here and this X term in here, so that is a common term in these two parts of the equation. So again, that varies linearly. So if we look at this point, let's just draw this up the top here for running out of room. But if we consider the point just at the point beyond where P is applied, so we've got P divided by 2 at this location and P coming down here, the internal moment here, sorry, let's keep that consistent, the internal moment here, mx, is given by, if we just imagine that we are infinitesimally small distance past that point, we have P divided by 2 times L divided by 2, and then minus P times essentially 0. So again, this cancels out and we end up with PL divided by 4. So that confirms, and it couldn't really be anything else, that starts at PL on 4, and then it steadily reduces as x increases, because we're subtracting more and more of this term from this term, which is our PL on 4. So that is gives rise to a reduction in that until we get to this point here, where x is equal to L minus L on 2 is L divided by 2 times P. So this gives PL divided by 2. And then this is P divided by 2 times L this time. So that's PL on 2 gives rise to PL divided by 2 minus PL divided by 2, which equals 0. So we're back at 0 at this point here. So this then is our bending moment diagram for a point load mid-span between A and B, with a maximum value at mid-span of PL divided by 4. Okay.